Okay, so we have our review. So 10.1, we talked about different ways of coming up with a list or some way of presenting the different arrangements for various scenarios. One was what was called a product table, and here's an example of one. So usually what you have on this row is numbers, and this row is numbers. We did it for dice, where we had 1, 2, 3, 4, 5, 6, and down, and then we came up with the different combinations or different arrangements of the two, like if you were getting 2 7s or 2 and a 7 and so forth. We also added the two together in these squares in the middle. So, you know, depending upon what the problem is asking for, you do a different thing. But like I said, let's say I put some numbers across here, and then I do some different numbers down here, or they could be the same numbers, it doesn't matter. So let's say I want to create or list all numbers which start with 1, 2, 4, and 5, and end with 2, 4, 7, 9. And start means the first number of a 2-digit number, and ends with these two. So what I would do is I would say, okay, the first number what I have here in this row, and these are the second numbers. So then I would just write out this. It's just a way of organizing the process of listing all these numbers. You could actually do it without going through this organized procedure, but organized is what mathematicians like to do mostly, just to keep things straight and don't get confused. See, I almost got confused there. So these all should end with 2, these should end with 4, 7, 9, and then we have 1, 1, 1, 1, 2, 2, 2, 2, 3, 4, 4, 4. Okay, so once you've filled out the product table, then you can ask questions. I might ask, list the even numbers. So I could look at it and say, okay, well, I have 12, 14, these are odd, and I would just go through the table and pick out the ones that satisfy the requirements of the question. I might say, how many non-repeating numbers are there? So then I would take this table and I say, okay, what do I have any ones that have repeating digits? And then I would say, okay, that one's got repeating, that one's got repeating, and I think that's it. So then I would just count them. I could count them all. I could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Or I could say, well, I have 16 total. I'm subtracting 2 out. So, you know, answer 14. So you basically use the table to generate the information and then answer the questions. Another way of doing this in a multi-step process is using a tree diagram. The most common tree diagram that we've dealt with is the flipping the coin. And so what we would do is you have a multi-step process which you model using this tree to list all the possibilities. So I'm going to flip a coin 3 times. So this first step, you list the possibilities that you could have gotten with your heads and tails. Then from this, you branch off and you say, okay, now I'm going to flip the second coin. What are the possibilities of flipping the second coin if I get a heads for the first? Well, because it's equally likely, I'm going to get heads and tails at that point. And the same thing down here. So those are my two possibilities, heads or tails. But that goes along with the first one being differently. Then you go to the third step. And again, because you're flipping a coin, I go off with two more branches like this. And again, the options for the third step are, again, heads and tails. And so to list out the possibilities instead of making it into into listing of possibilities through a table, what you do is you just go through down each branch. So the top branch here would be heads, heads, heads. The next would be heads, heads, tails. Then we have heads, tails, heads. Then we have heads, tails, tails. So those are the first four. Those are the four with heads being the first choice. And then you have the same thing happen to the next three ones. So you have tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. So those are, again, we're specifying exactly what all the different arrangements are. And then I could ask you questions about, list the ways to get all heads. Well, that's pretty easy because there's only one case where you have all heads. I might ask you list the ways to get exactly one head. So then you look through here and ask the question, which ones have one head? And you'd say, well, so far they've all got two heads, and they get to this one, so that one has one head. So that's good. That has two heads, that has one head, so write that down. And then the final one here, I've had tails, tails, heads. So those are my three. You can see the heads is in the first place, second place, and third place. So again, that's the tree diagram. So be able to construct one. I want you to be able to evaluate these types of ratios of factorials without using your calculator. So what I'm looking for you to do, we've done this a bazillion times, is to rewrite the numerator as the factorial written out. Until you get down to whatever factorial this is. So you go down 6 and 5 factorial, then you'd write factorial in the denominator, and then you'd mark through those, and then you have 9 times 8 times 7 times 6, and then you plug that into your calculator, and you would get an answer. So we had quite a few homework problems with that. We've done it in class so many times. If you don't get that, you're in trouble. Okay, so we just get a number. So I don't want you to just give me the number. I want you to go through the entire steps that I show here. You could have something like this. So in this case, what you do is you take 10 times 9 times 8 times 7 factorial. You'd pick the larger one of these two. I'm going to change the order in the denominator so I can match these two up. That becomes 1, so you end up with 10 times 9 times 8 divided by 4 times 3 times 2 times 1. And I didn't pick these because they were permutations or combinations. I just picked numbers. So it could end up being a fraction if you don't have to necessarily get that. If you're doing a permutation problem, it should come out to be a whole number. In this case, it does work out okay. So you get 30 is the answer. So again, you show all the steps to get to that point. Okay, then you want to be able to do the fundamental counting principle. Everything comes down to the fundamental counting principle. And some problems you may be able to answer using permutations or combinations, but I want you to have it where you can explicitly choose something. So let me give an example. I have 10 people to choose 3 officers for a club. Using fundamental accounting principle, how many arrangements are there? Now, you might recognize this as a permutation problem because I have officers, which order is important. I have 10 people to choose from, 3 people at a time, so I could solve the problem just by saying 10 permutations of 10 things taken 3 at a time, and that would give me the correct answer. Of course, you would do n factorial over n minus r factorial. But using the fundamental counting principle, what I would say is there are 3 steps. 1, choose president. 2, choose secretary, whatever the officers are. I didn't say what they were in the problem statement, but choose historian, just to be different. We're not dealing with money. So those are the steps. So what I would do is then I would think about the process. This is president, this is secretary, this is historian. And I'd say, okay, fundamental accounting principle says that I look at the first step and I see how many choices I have. Well, you go to the problem, you say, okay, I have 10 choices for president. Because I'm doing officers, and you can't be multiple officers, so there is no substitution, well, not substitution, but I can't repeat things. Then I'd say, oh, for the secretary, I've got 9 people to choose from now. And then when I get a historian, I've already chosen 2 people, so 10 minus 2 is 8. And so using the fundamental accounting principle, I get 720, which is the same answer I would get here. But I want you to spell out a little bit more about now, that's using the fundamental accounting principle for a officer. But let's say if I want a committee, or cards. So another example, you pick cards in the order. You can think about lottery. All those cases, the order doesn't matter. So all of those, you would use combinations. So the fundamental accounting principle, in that case, let's say I have 10 people, and I have 4-person committee. Again, because of this information, I could solve it as a combination problem, but the fundamental accounting principle would say the number of arrangements where order is important would be 10 times 9 times 8 times 7. So what I've done is, when I picked the first person, I had 10 people to choose from. When I picked the second person, I had 9 people to choose from, and so forth. And I did that 4 times, so you get 10 times 9 times 8 times 7. That's 5,040. But 4 people can be arranged how many ways? Can be arranged basically 4 factorial. What I'm doing there is why is that? Because when I pick 4 people, the fundamental accounting principle would say, okay, I'm going to have 4 choices for the first slot for the 4 people. The next slot is 3, 2. I go all the way down to 1 because there are 4 slots and there are 4 people. So I multiply those together and I get 24. So there are 24 arrangements. For a given 4 people, there are 24 arrangements. So the number of committees where order is not important is 5,040 divided by 24. And I get 210, and that's the answer. So be careful. It could be either this kind of problem, it could be this kind of problem. Fundamental accounting principle. It might involve committees, it might involve cards, it might involve the lottery. But again, this, if I had 9 people taking 4 at a time, I'd still divide by 4 factorial because I'm always asking the question, if I have 4 people, how many different ways can I arrange those 4 people? But in reality, all those different arrangements don't make any difference as far as committees are concerned or cards, hands are concerned. So that's why I have to divide by this number. Okay, and then there'll be some pretty much straightforward permutation or combination problems. And for those, they may be single-step ones, which should be fairly easy to do. So, remember when order is important, that's when you use permutations. When order is not important, then you use combinations. So look for those key words. This is order is not important, permutations. And if order is not important, so things like I said, officers, lineups, like in a baseball or a music event, that's important. Race, positions. Whereas combinations, again, we're talking about committees, sampling things, samples. If you're looking for defects, games, we did that, where you're 2 teams are playing. It doesn't mean whether it doesn't matter whether we say team A plays team B or team B plays team A. It's the same game. So when those are the cases, you just use the appropriate permutation or combination formula. You'll also just be able to, I might give you something like this, and you have to come up with the answer. And again, you're not allowed to just put the answer. What you would do for something like this is you would write the formula first, which is n factorial over n minus r. So you can write those down as your formulas. What you would write down is p with n and r, and then you would write that. So that's the formula you want to write. So then you write, to do this part of the problem, you just look at that and then you just substitute it in. So n is 9 and r is 3. So that's the first thing you do, is plug in the 2 numbers here. Secondly is you do the math. like that. Then you in this case it's easy because there's only one number in the denominator. That's the number that you rewrite the numerator in terms of. So you start at 9 and then go down by ones till you get to whatever the factorial the denominator is. Those two will then cancel out, and you'll have 7 times 8, 9 times 8 times 7. 9 times 8 times 7 is 504. So make sure you do that, as well as the combination ones. You have those 12 things. 9 at the time. You would write out n factorial over r factorial times n minus r factorial. You write that in your book, in your cheat sheet. So you'd have 12 factorial over 9 factorial times 12 minus 9 factorial, which would be 12 factorial over 9 factorial, 3 factorial. And then you could write the numerator as 12 times 11 times 10 times 9 factorial. You pick the larger of those two so that you can group these two together, cancel as much as possible. Then you end up with 12 times 11 times 10, and then you write out the factorial that you have left. And then you can plug in the numbers where you can simplify. And I get 220. Okay, so make sure you can do that by hand. There may be also another fundamental counting principle problem, which is a lot easier than a lot of people think. So I'm just writing this down again. So, we have these multiple step processes, and we did those this week. For example, when we did the choosing the people for the lineup for the musical recital, that was one thing we did, where we picked the boys and then we picked the girls. And that was a two-step process. You can also get even simpler if you want to say, you have 5 dogs and you have 7 cats. How many arrangements are there? And in this case, the order is not important because if you pick one dog and a cat, it's still the same cat and dog. So you would want to take that into account. So the way you would do that is you would say, okay, I've got a two-step process. I'm going to pick a dog. I'm going to pick a cat. I'm just going to pick one cat and one dog. So when you're only picking one of many, you don't have to use combinations or permutations. You just take the number that's here. So I have 5 dogs and I have 7 cats. Now, is order important in that the way you've done it there? Just thinking about that. I don't think so. Just thinking about that. If you yeah, so it would just be 35. Now, let's say if the order is important. If it was a cat, then a dog, or a dog, then the cat, how would that increase the number? How would that change that? So let's say order is important in how I'm choosing these. So what you would actually have is a 3-step process now. You'd pick order, you'd pick dog, and you'd pick cat. Or you could pick the order, and you could pick the cat, and then you could pick the dog. So you're saying, what am I doing here? But the thing is that here I'm just picking the dog and picking the cat, and then I use that information here to pick the dog first. So let's say I pick the dog first here, then no matter, so what I would do is I would list the dog first and the cat second. If I want the order to be cat instead, then I would pick the cat first and then the dog. So there's two different ways of that going. So where order is important, I would pick the order first. Dog, then cat, or cat, then dog. Those are two orders. And then from that, I would pick 5. I'd have 5 dogs to pick from and 7 cats to pick from. And so you would actually have 70 total arrangements if the order of the cat and the dog was important. Okay, so there's going to be something that will be similar to that, not exactly to that. Okay. Then we have the case of, let's say you have 10 dogs and 6 cats. And I want to pick 3 dogs and 2 cats. And ask how many different arrangements of those 10 dogs and 6 cats. Well, this is like a committee, because I pick the 10 dogs. It doesn't matter what order the dogs are in. I just want to know they're dogs. So this is going to be a combination problem, and this is going to be a combination problem. But then I have them together. So for each combination I pick over here, I can have X many of combinations on this side. So the way it works is you take 10 things 3 at a time here, and you multiply by the number of arrangements you get by taking 6 things 2 at a time, and that will give you your answer. So that would be 10 factorial over 3 factorial times 10 minus 3 factorial. This would be 6 factorial over 2 factorial times 6 minus 2 factorial. Carry out the math in the parentheses. Then I would rewrite 10 factorial as 10 times 9 times 8 times 7 factorial, because that's 7 factorial is the larger one. It's going to cancel out and become 1. Here I do 6 times 5 times 4 factorial. Those become 1. So I'd add 10 times 9 times 8 over 3 times 2 times 1. That's 3 factorial. And 6 times 5 times 4. I actually don't need the 4 because I can cancel that out. 6 times 5 divided by 2 factorial, which is 2 times 1. And you can simplify that, or you can just multiply it out. 10 times 9 times 8 times 6 times 5 divided by 3 times 2 times 1 times 2 times 1. You can ignore the 1s if you want to, and you get 1,800 arrangements. So, problems that we've done, the case of picking committees of Democrats and Republicans, that's another example of where we did that. So what we have is basically, if we go back at the top here, we have 2 committees basically, or 2 samples. These are really just like samples where the order is not important. So we can use combinations to get each part of that. If I had a third thing to choose from, then I would say cats, dogs, and rabbits. Well, the rabbits would be a separate combination thing. Okay, radio call letters. We did that. That's using the fundamental counting principle. And, there were restrictions on it. We had one for homework. We talked about it in class, so I'm not going to go over it, but there is one that involves that. Basically there was some, rules, like there were 2 choices here, W or K. And then the next couple letters, depending upon if you allowed repeats, you would do this. If if you didn't allow repeats, then including W or J or K, then you'd have 25 here, and then you'd have 24, and then you'd have 23, because if I choose one letter here, then there's only 25 letters left over. And then if I choose the next letter, I can't use two of them, so there's 24 letters left over. So this is a direct example of the fundamental counting principle. Then there's going to be one which uses the complement principle. You can look at your notes about that, but the key thing, the one we looked at the most, involves coins, flipping coins. So it was the use of the word at least. So at least one head. And what we did is we found the opposite of that. At least one head, the opposite is at least one head is no heads. If we said at least two heads, then the opposite of that would be one head or no heads. So that's how you have to make sure you understand what at least means. It means the number and greater. So the opposite is less than the number. So in the case of less than two heads is one or zero heads. And the complement principle basically says we find out, let's say we flip 9 coins. So in this case, it's a multi-step process. Each time you're using heads and tails. So if you flip a coin, it's always 2, which is the two choices, heads or tails, raised to the power. So if you have 9 coins, you take 2 to the 9th power, which is 512. So that's the total number of possibilities. The complements principle says that if you have one of these at least cases, instead of answering this question, if you wanted to know at least one head, what you would do is you get the total number of arrangements minus the number with no heads. So at least one head, take the total number, subtract the number with no heads, that'll get that difference. So in this case, you'll get 2 to the 9th minus 1, because there's only one case, all tails. If you had at least 2 heads, what would happen there is you would have 512 minus 1 again, because you have no heads again, and there are actually 9 cases where you have one head. So it's always that arrangement. Whatever this exponent is, that's the number you put here, because you can have the head in the first place, first flip, second flip, third flip, all the way through the 9th flip. So there's 9 of those. And so at least 2 heads, you take the total number, subtract the opposite, which consists of 2 parts. So that would be 502. This one would be 511, because 2 to the 9th is 512. So that's how these at least complements. Same kind of thing in a sampling problem. The sampling problem is a combination problem. So what is an example of this kind of problem? It was the problem we did in class with the, what was it? Les Miserables and Phantom of the Opera. And there were 10 plays. And they're asked how many arrangements, if I pick four out of the 10, how many arrangements have at least one of these? So the opposite of at least one of these was none of these. So what we did was we found the total number of combinations taking 4 at a time. So we had 10 plays, including Les Mis and Phantom. So this gave us the total number, and then we subtracted the total number of arrangements where we didn't include these. And that answer is the number of groupings that contain at least one of the 2 plays that we discussed above. So if you were doing a sampling, let's say you sample 50 items, and 4 out of the 50 are bad items. There's a defect. So the question is, how many arrangements have at least one bad item? How many samples that you take of the total possible? How many samples have at least one bad item, defective item, question mark. So again, what you would do is you would take your 50 items, your total number, and you would actually, so we have 50 items for sample. We got one more thing. Let's say you take 8, you sample 8 out of there. Sample 8 out of the 50 items. What's the chance? What are the number of possible samples out of the total that have at least one bad item in it? Okay, how many samples have at least one bad item? So you would have 50 items. This is the total, including the ones that have the bad, including the 46 that are good, and you would take those 8 at a time. So that would give you the number of samples, 8 sample subsets. And then you would subtract off the number of samples, subsets that don't contain the bad ones. So what you would do is you'd subtract 4 from 50. You get 46, and you take 8 at a time there. So this is the number of arrangements or groupings that don't include the bad items. And the difference between those two would be the answer. Now, since I picked a large sample size, these numbers would be fairly big and calculate, but the basic idea is the same thing. If you're dealing with a sample, you have the number of samples, number of things you're going to sample from, the total number of boxes. You're going to randomly pick 8 of those boxes. Out of the 50 items, 4 of them have bad items in it. So how many samples have at least one bad item? It's the total number of possible combinations, which includes the bad items, minus the number of combinations where you've removed the bad items from the possibilities, still grouping them 8 at a time, and that difference will give you the answer that you're looking for. Then you have this question of OR, and the OR question. And what that said was that the number of samples of A that satisfied A or B is equal to the number of samples that satisfied A plus the number of samples that satisfied B minus the number of samples that satisfied A and B requirements. So you want to be able to use this formula. The big example we use with cards, where you've got suits and you've got values and you've got face cards. So, if you pick so many cards out of a deck, out of those 52 cards, how many satisfy these OR requirements? So let's just give you a question. So that question is, out of 52 cards, and you pick how many of the cards are, if you randomly pick, if you pick all of them, all the different cards that you do, the question is the number of ways it could be a 2 and a heart, or heart. It's not and, or heart. So I'm going to pick a card, 52 cards. How many different ways out of the 52 can it be a 2 or a heart? So what you do is you find the number of cards that are 2s. So in this case, N sub A, N of A is, they're going to be 4 2s because there are 4 suits. Then you have B, which is the number of hearts, the second part of the OR statement, and there are 13 hearts. Then you ask the question of, where do I have cards that are both hearts and 2s? And the answer is yes, there's one of those. There is a 2 of hearts. So there's one of those where it's both of those. So to answer the question, the OR question, the number of ways it could be a 2 or a heart, you take 4, N of A, 13, which is N of B, subtract off where you had and you do the math, you get 16. So 16 out of the 53 cards is going to be either a heart or a 2. If you didn't subtract 1, you would be double counting the 2 of hearts. And the final question is, write out opposite statement. This goes along with these examples. For example, here, the opposite of at least one head, the opposite of that is no heads. You can kind of write it in mathematical terms. So at least one head would mean X is greater than or equal to 1. So what is the opposite of greater than or equal to 1? Well, X is less than 1. And because you can't have negative heads, that would be the same as X equals 0. So the opposite of at least one head is no heads. This one would be at least 2 heads. So X is greater than or equal to 2. The opposite of that would be X is less than 2. So that means X has to be equal to 1 or 0, again, because you can't have fractional heads. So you can do it mathematically, and then you can kind of rewrite it out. So if I said, what's the opposite of the statement if you roll a fair dice 3 times, in how many ways can you obtain at least one head? Question mark. So how would you say that? What's the opposite of that question? Because you'd use that in the complement principle. So you'd say, okay, how many ways? Let me just say X means how many ways. How many ways can you obtain at least one head? At least means greater than or equal to whatever this is. So the opposite of that would be x is less than 1, which would also mean that x has to be 0. So then I would write it in words. So the opposite statement, if you wrote it out, if you roll a fair dice, I don't know, it looks like face dice, but it should be fair dice, 3 times, I forgot to write times. If you roll a fair dice 3 times, in how many ways can you get, and it should be heads. So let's say at least a sum of 3. 4, let's put 4 in there. So I have to go back, I'm getting confused between dice. So let's start over again. If you roll a fair dice three times, and you add them together, in how many ways can you obtain at least a sum of 4? So at least 4 means greater than or equal to 4. So less, the opposite is less than 4. Well, if you roll a dice, the minimum you're going to get is 1. So the least you can get is 3. So instead of x is less than 4, I could restrict it to x equals 3. That's the only choice I have that's less than 4. So if you roll a fair dice 3 times, in how many ways can you get a sum less than 4? That would be the opposite statement. Or you could say, or a sum of 3. Either one of those would be the opposite, and that would be what we would use in the complement principle. So that's it. You can bring a cheat sheet, one cheat sheet, your calculator. The key thing is you got to remember to write out any work that you do that shows the calculations for permutations and combinations. I'm not going to let you use it. You can use your, if you have a calculator that has the functions, you can use to check your answer, but you need to show me how you get it without using the built-in function. Need to recognize when you have permutations and combinations, where order is important, where order is not important. There are certain things that I pointed out that should be key. If you have a multi-part process, then you look at each part of the process separately and then multiply those arrangements from each step. They may be just simple steps where you're just picking one out of a multitude or out of a certain number of things. There you just multiply the number of options per step. Or you may have something like the case where you're picking the dogs, 2 dogs out of 5 dogs. So if you're picking more than one thing, then the steps may be involved using combinations. You may have a sub-step involving the counting principles or using combinations or permutations depending upon what's asked for you. So that's it.